Okay, so for an introduction to group theory, we're going to first go over the definition of a group. So here I have that we say that a set G, so we have some set that's, whatever, it could be anything, but it's just a set of elements, right? Whatever they be in here. And then we have a binary operation. Okay, so a binary operation is something that takes two elements and then produces a third element when you combine them with this star. So for example, addition is a binary operation because you take two numbers, whatever, 2 and 5, and you add them and then you produce a new third number, which is 7. Or multiplication is a binary operation. Division is a binary operation, but it never will work for a group. But anyways, you have some binary operation, you take two elements in the set, and basically you need it so that way all of these conditions are met. And there's names for each one of these conditions. So you have that, okay, again, you got a set, you got the binary operation, and it forms a group whenever for all the elements in the set, when you do one element and then you do the operation with the other element, the resulting element, this here, is still within the set. So you get another element inside the set. This is called closure. Okay, we say that the set is closed under star. We say the set G is closed under star. So for example, like if you take Z, the integers, right, to be G, and then we take addition to be the operation, then we should see that the right, we say that the integers are closed under addition, right? If we changed this around, this sentence, right, we say that the set of integers Z is closed under addition, because if I take two integers, right, I don't know, -3 plus 11, right, I for sure get another integer, right? Okay, and I'll always do that for any two integers. N plus m is always then another integer. And this has to be true for a group. This is called closure. Okay, now the next one is that there has to exist what's called an identity. So this second one is called identity. Okay, there has to exist an identity element in the group. So you have to have it that for any, okay, for all x contained in G, this condition is true. That if you take, for example, in the integers, right, any integer m, and then we do plus 0 is equal to m, the original integer, 0 plus m, and then this is the identity element. And you have to have this for any group that's formed. And I'm using the example of the group formed under addition for the integers. And then the next condition is that you need it such that for all G, there exists some other, for all X in G, there exists some other element in G with that when you perform the operation, you get back the identity. So if we continue with our example, right, 5 plus -5 equals 0, which is the identity element in this, and then -5 plus 5 equals 0. Okay, and this is called inverses. It must have inverses. Okay, and then the last one is associative. Okay, it must be an associative thing, so that way you don't need to put parentheses, right, anywhere. That this is just, you could just write this as x star y star z. The parentheses are unnecessary, just like sort of like how they're unnecessary if you're adding integers or whatever it be. You need associativeness to be true. That for all x, y, and z, you can, put the parentheses here, perform what x star y is, and then get that value, and then do star z. Or you could do x star, and then find out what y star z is, and then do star x star, whatever y star z is. Now, what we're going to do is we're going to prove that the set of all 2 by 2, so this is false. The set of all invertible, and this is a key part, invertible 2 by 2 matrices form a group under matrix multiplication. So we need to have an idea. First, let's leave this aside. Let's not worry about invertible. I'm going to define that as we go. But the next thing is matrix multiplication. So what's the proof? So what do we need? We need it so that way if I multiply, so what's the set here? The set is all, let's say S is equal to, right, set of all invertible two by two matrices. Okay, that's S. So I want to take any two of these. So if I have two, whatever, A, B, C, D, and then I do matrix multiplication, E, F, G, H. This is for sure another 2 by 2 matrix, whatever it be, okay? And that's easy to check. So that's 1, right? So how do we do the matrix multiplication? I do this times this, right? What do I get? A times E, this is A times E plus B times G. And that would go right here, and then you would do this times this, and you would get the element for here, and then you would do this with this one, and you would get the element for right here, and then you would do this with this one, and you'd get the element for right here, and you for sure get another 2 by 2 matrix. Now the key is this an invertible 2 by 2 matrix? So we would have to make sure that if I multiplied two invertible matrices, that I get another invertible matrix, which I have not checked because I have not defined this idea. But let's just, for the time being, because we'll get to the idea of invertible in a second. So we want to have an identity element. So this is easy. So this is 1. Okay, and we're gonna like sort of shelve that for a second. We're gonna come back to it. But 2, right, is that we need an identity element, and we should see that if I have any matrix, it doesn't even need to be invertible, we don't need to worry about it, and I multiply it by this 2 by 2 matrix, it will equal, if I change the order around, and it will be the original matrix. Okay, why? You can check. Well, A times B, AB times this one is just A. And now I'm doing the actual thing. A times 1 is A, plus 0 times B is just A. Then I'm going to do this times this to get this one. And then I'm going to get 0 times A is 0, plus B times 1, that's just B. And then I go on to here. C times 1 is C, plus D times 0 is just C. And then C times 0 is 0, and then D times 1 is D. And you need to know how to do the matrix multiplication in order to see that this is indeed, you get back the original, which is this idea right here, right? This is 2, right? Match what I just did with this definition here. There exists an identity, so look, this takes the role of E, this is X, this was any invertible or any matrix really, and I got back X, I got back the original matrix. And you can show this way, right, the other way. This times this is going to give you A, this times this is going to give you the B here, and then this one times this one is going to give you just C, and then this one times this is going to give you just D. And it is indeed the case that we have it, that there's an identity element, which is this 0, 1, 0. This is identity. Then you want to check that there's inverses. And this is where we want to make sure that, hence the word invertible, 2 by 2 comes into play. And we actually want to make sure that if I multiply 2 invertible matrices, then I get another invertible matrix. So let's do 3 now. So 3 is going to involve some extra work here. We're going to do I'm gonna get another piece of paper and we're gonna start going through this. So, okay, let's take a 2x2 matrix. Okay, and what you do is you want to do row operations till you get it in the form 0, 1, like this. And it's just going to be like some algebraic task. And you keep track of everything that you do on the one side. So what I'm going to do is I have this, and then I'm going to have the identity on the other side. And that's going to keep track of everything that I do. So I want this A to be a 1 to start. So I'm going to divide everything by 1 over A. And that's going to be 1, B, and then this is going to be 1 over A, and then this is 0. Then I'm going to, since I want this to be a 1, now I want what? I want the C to be a 0, so so let's leave this the same. So I want the C to be a 0. So what I'm going to do is I'm going to multiply this by negative C and then add it to the second row. So when I multiply by negative C, right, this becomes negative C. This becomes negative CB over A, negative C over A, and then 0 still. Then I add it. I'm going to get what? This top row stays the same. I'm going to get 0 here. And remember, this is D minus CB over A. And then this was negative C over A, right? 0 plus negative C over A. And then this just stays 1. And now I need to get this to being 0. So what I'm going to do is I'm actually going to first make this 1. So what do I need to do to make D? So let's just do the math on the side. D minus CB over A is the same thing as DA minus CB over A. So if I want to make this 1, I need to multiply by A over DA, or AD minus BC. So I'm going to multiply the bottom row by the reciprocal of this, which is A over AD minus BC. Right? When I multiply this row by that, this stays 0. And then I'm going to get 1 here because I multiplied by the reciprocal. And then when I multiply this A cancels with this A. So I'm just going to be left with negative C over AD minus BC. And then over here, I'm going to have A over AD minus BC. And then the only thing now I need to do is get rid of this to being 0. So the way I do that is I multiply everything by negative B over A. Right? So I want to multiply the second row by negative B over A. And what am I going to get? I'm going to take my time with this because it's negative B over A this is the second row. And then I'm going to get BC over A, AD minus BC. And then this, when I multiply by negative B over A, I'm running out of space, negative AB over A, I'm multiplying by negative B over A, so it's B minus BC, right? Did I do this right? B times A. And then that's the second one, and I gotta add this to the top. So I'm gonna get 0, and then it's 1 over A, right? Because I'm taking this, right? Yeah, 0, right. And then this one is added to the 1 over A, so it's this. Okay. and then the 0, it's negative AB over AB minus it's AD over BC, yeah, AD, that's a mess up, AD, and then this stays the same, 0, 1, negative C, AD minus BC over AD minus BC. And then now I'm going to try and simplify, because this matrix over here now should be the inverse of the original matrix. And if we did this right, this is how we do it. Now, what is this matrix? Let's see. We get 1 over A, and then 1 plus BC over AD minus BC. Okay, this becomes 1 over A, and then I'm going to get a common denominator here. AD minus BC plus BC over AD minus BC. All right, take your time on how I did this. This cancels with this, and then you're going to be left with an A, and it's just D over AD minus BC as this first coordinate right here. All right, so that's the first coordinate. I just did the algebra. Then this one, the A's can cancel right away. It's going to be negative B over AD minus BC. Then this one's negative C over AD minus BC. And then this one's A over AD minus BC. And then this is the inverse matrix. Now, what's nice about this, okay, and again, just sit here and get to this final point. Let's write it again. Let's write the final answer that we got here. So the final answer, I argue that A, B, C, D multiplied by, what's the inverse of this? So the inverse, again, just sit here, do this algebra correctly, make sure, and let's check it together. Let's see. It's going to be D over AD minus or plus minus BC. Minus BC. And then what's the other coordinates? Let's see. So it's only negative B, negative CA. Negative B, negative CA. And again, everything is over AD minus BC, and that becomes key. AD minus BC over AD minus BC. Okay, and let's check. And what I should get here is 1, 0, 0, 1, the identity. Okay, because I want this to be the inverse of ABCD. So what do I get? Let's check. So I'm going to do this times this. Or, multiply the row times the column. So it's A, D over, and this should be 1, right? AD minus BC, okay, plus, okay, negative BC over AD minus BC. And then this becomes AD minus BC over AD minus BC, which equals 1. So we're good so far. That's good. Then the next thing that I need to check is that this should be 0. So let's see. A times negative B is negative AB. And then B is plus BA, and it's all over AD minus BC. But though this is the same as that, so we get 0 over AD minus BC. And then this is indeed 0. And then I do this times this one, right? CD over AD minus BC again, plus something over AD minus BC. What is it? It's D times negative CD, and then of course this is just the opposite, so I get a 0 here, and then this times this one, right, is negative BC plus DA over AD minus BC, but you should see that these two things are actually the same, so they equal 1. The numerator is the same as the denominator, and I get 1. And yeah, that's one way. I would technically have to check the other direction if I wanted to do it. I would have to do this inverse, okay, here times this, and I would also see that I'd get the identity back. But the point is that this is the inverse. Now the question is that when is this bad, right? Let's take a look at your general inverse, right? Because that's going to be able to classify all the invertible matrices. So I have 1 over AD minus BC as a scalar, and then it's D minus B minus C, and then A. Okay, this is the inverse of the matrix ABCD. Now, when does this matrix ABCD, this matrix A, let's call it capital A, whatever. Okay, when does this matrix not have an inverse? Well, it doesn't have an inverse if you're dividing by 0 here. And that's a statement for all the invertible 2x2 matrices. So we could say that a 2x2 matrix has an inverse, okay, or is invertible, same thing, right? Or is invertible if and only if, okay, the 2x2 matrix is matrix ABCD has an inverse if and only if AD minus BC does not equal 0. Okay, and we could prove that, okay? If this is not 0, right? If this does not equal 0, then this is its inverse. And we could say that, right, so what's the directions? We need to say that if AD minus BC does not equal 0, then this is the inverse. Then we want to say if it has an inverse, then we can't have this equal to 0, right? Because if it does, then this would be its inverse and so forth. But this is a true statement. This is the idea, okay? We should be able to see why it's true in both directions. And this is what we mean, okay, when we say all the invertible matrices. Now what we need to prove is that if I have 2 like this, that when I multiply them again, I get another invertible matrix. But that's sort of obvious because if you have EF minus ABCD, ABCDEFG, right? So this is another matrix, right? And I multiply it by ABCD, I want to prove that the resulting matrix doesn't have it that this one times this one minus this one times this one equals 0. And you can prove that algebraically. So closure takes actually a long time in this case. So let's actually see. Let's actually go through it. It's worth going through how tedious this can be in proving something as a group. So let's say we have 2 matrices that are both invertible. So we have A, B, C, D, and then E, F, G, H. And we know AD minus BC does not equal 0, and EH minus GF does not equal 0. We want to show that the resulting matrix has it so it's resulting, that this moved over. So let's see what I mean. So we go A, B, E, G, right? What am I going to get? A, E plus BG for that one. And then A, F plus BH. And then I'm going to do CD, CE plus DG, and then CF plus DH. And what I want to prove now is I want to prove that this times this minus this times this does not equal 0. So let's see, AE plus BG times CF plus DH minus CE plus DG times AF plus BH. I want to prove that it does not equal 0. So the only way I see to do it is by multiplying everything out and then combining the like terms. It's probably the only way. ACF plus, right, so plus AEDH plus BGCF plus BGDH minus CEAF. And is everything going to be minus here? Yeah, everything will be minus here. So minus CEBH minus DGAF minus DGBH. Okay, and now I'm going to rearrange. I think that I need to somehow use these facts, right? And what I think is crucial, actually, so we need to know some other facts. We need to know that if both of these are non-zero, then the multiplication of the two of these is also non-zero. And that's how I'm going to get the fact. So I know that this, from these two facts, I know that the multiplication of these two is also non-zero. If they're both non-zero, then the multiplication of them must be non-zero. These are now just, integers or real numbers. I could have taken it over the reals, which is fine. Let's take it over the reals. Let's say A, B, C, D, E, F, G, H. That, this is the set of 2x2 matrices with coefficients in the reals. Should have been a little bit more precise, but it's okay. So I'm going to get A, D, E, H minus A, D, G, F minus B, C, E, H, and then plus B, C, G, F does not equal 0. Okay, now let's match these. So let's see. I know A, D, E, H, this, minus I need an A, D, and this. Okay, so this, and then a minus B, C, E, H. B, C, E, H. Okay, here. So this, and then B, C, G, F. B, C, G, F. Okay, so all of this, right, I know is non-zero. Now, how do I get that the other part is non-zero? Well, let's see. I know that this... Wait, is there more than one of these things? Is this all... Oh, there's another one, right? Oh, this C, E, F, A, C, E, F, A is the same thing, so these cancel. Nice, okay. And then this is the same as this, and then I get that this... With this, I just showed you that when I multiply two non-zero numbers, I must get something that's non-zero. And then I get here, and then this is non-zero. And you know that the multiplication of two invertible matrices is another invertible matrix. And there you go. Yeah, so this is the whole idea. Let's go back to the beginning. Let's make sure that we're back. Let's go reorganize ourselves, and this is something that you got to stick with. So the first thing is that I wanted to show closure, that for any invertible 2x2 matrices, so this is, let's say, an invertible 2x2 matrix, and then this is an invertible 2x2 matrix, I needed to show that this was an invertible 2x2 matrix. And I did, because I took here, right, this was some invertible 2x2 matrix, this was some invertible 2x2 matrix. How do we know? We know because this doesn't equal 0 and this doesn't equal 0. And I showed that for the inverse, right, in this one, I computed the inverse of this matrix. Okay, and I got this here. Okay, and the key here was to notice this statement, that this matrix, right, A, B, C, D, has inverse if and only if AD minus BC does not equal 0. And we should just convince ourselves of that, right? Why is that true? It's the one direction that's sort of tricky right now for me. So the first one is that if, right, has inverse, right? Well, if it has an inverse, its inverse is this, AD minus BC times, right, D minus B, C minus CA. That's its inverse. Right, so it must be then that AD minus BC does not equal 0, because you can't have this here being equal to 0. You can't divide by 0 even in this context. So yeah, that's the one way. And then the other way, it's clear that if this doesn't equal 0, then its inverse is this. So this is the if and only if statement that we needed. And then once I have that, then I show that, okay, these are two invertible matrices. So then that means that this must be true, right? Because the inverse of this one has that 1 over AD minus BC in it, and this one has the EH minus FG in it for its inverse. So if these are two invertible matrices, right, then this must be true and this must be true. And this is saying that this is non-zero, this quantity here, whatever it is. And then this is non-zero, whatever this quantity is. And when you multiply them two non-zero things, you also get something that's non-zero. And then I just did the matrix multiplication, and then now this takes the role of the new whatever, alpha 1, alpha 2, alpha 3, alpha 4, and the, alpha 1 times alpha 4 minus alpha 2 minus alpha 2 times alpha 3, right? This is what we want to check. We want to check that this is non-zero, right? So I did that over here, right? I did that right there. And then I got this long thing here. I saw that some of the things canceled, right? This with this, and then this with this one. And then what I was left with was this. But this is just this right here. And this must be non-zero, because these two things are non-zero. So then this must be non-zero, these things that are left. And then that means that, by what we said before, that this is indeed an invertible matrix. And we showed that there's inverses. And we showed that there's, what did we show with this one? This is the second one? Oh, we showed that it's closed. Right, that's the first thing. We finished this. And then we showed that there's an identity. That's easy. Now the third thing we needed to show is that there's inverses. This is done. That's where we went on our side quest. And then associative we could easily show as being that, if I have three matrices, A, B, C, D, right? Let's talk about association for a second, just in this. So we finished this completely, so you have a good idea. So you have three matrices, A, B, C, D, E, F, G, H, I, J, K, L, right? If you have three, right, basically what it says is that if you do this first, right, you're going to get another 2 by 2 matrix. And then if you do I, J, K, L, right, you'll get some final matrix, and it needs to be equal to is if you did the other one first. So if you did ABC and then you left that alone, and then you did E, F, G, H, and you found out what this was, right, you're going to get the same thing. And we could check that easily, that this, right, will give you some other 2 by 2 matrix. And then you do A, B, C, D. With that 2 by 2 matrix, you're going to get that these two matrices will be the same, whatever it be. And that's showing associativity, that it is indeed associative, this operation. So again, this is a lot. This is good that we went through this, or that I went through this. That I went through this, or that we went through this, okay, because it just gives you so much. And you should try to see if you could show that, like, Z under addition is a group, and there's a whole list of groups, but it's just giving you that many mathematical structures form this group, okay? This idea of a group, and this is one of them, right? You could do many. There's many different ones, and you want to prove, you want to see, someone tells you, is this a group under star, whatever star is, right? Does this set of objects, does this set of numbers, does this set of whatever form a group under this operation? You want to be like, okay, let's go through this. And that's what I did for this set. I said the set of all invertible 2x2 matrices form a group under matrix multiplication, and I checked all these conditions, and then you could say yes, this is a group. And that's basically your introduction.